Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for differential calculus, and it is your first step into the limit laws. We're still not into the true definition of a limit. Traditionally, when you're learning limits, you kind of learn them at a 30,000 foot level. So you're very elevated above the true definitions. But then as you get closer to the true definitions, you learn what are called the limit laws. This just allows you to evaluate limits in the meantime prior to actually knowing the true theory. Let's go ahead and dip into them. Where we left off in the previous video series was with conceptual investigations of limits, and these can be really helpful. However, they're not the best way to actually evaluate a limit because there are some faster ways to, evaluate limits. And that's where the limit laws come in. Here are the limit laws right here, and I'm just going to scroll through them just to show you. There's quite a few. Don't be overwhelmed. Actually, you're going to get so used to these, they'll become kind of second nature to you. However, there's one piece that, even though it's not in that laundry list of properties here, there's one initial statement that most people forget. Pretend as though c is a constant, and we are considering the limit as x approaches a of f of x, and the limit as x approaches the same value of a for a different function g of x. And let's suppose that both of these limits exist and are finite. Now, in the previous video series, I said something about existence of a limit. When working with a limit, there are three possibilities of what will happen. Either that limit becomes something finite, or it becomes something infinite, or it ends up being something between finite and infinite. It doesn't become a constant like 3 or 5 or negative pi or something like that, and it doesn't become infinite like positive infinity or negative infinity. It's in nowhere land. It's what we call DNE. It does not exist. If you have a limit that's neither finite nor infinite, it just doesn't exist. However, I mentioned it in the previous video series, if you have a limit that is finite or infinite, we say that these limits actually do exist. So if I tell you that you're working with a limit as x goes to a for some function f, and you know that limit is finite, not only do you know it's finite, but it exists. If I tell you you have the limit as x approaches a for some function f, and that limit, I tell you, is infinite, it still exists. It's just infinite. On the other hand, you have that middle ground where the limit just doesn't exist, where it's neither finite nor infinite. Now, that being said, going back to this theorem, if we have a couple limits and we happen to know both exist, that tells us it's one of two situations. The limit's either finite or infinite. However, there's an additional condition. They have to be finite. So both of those limits must be finite for us to use the limit laws appropriately. So I am going to go ahead and cross out the infinite case. Now we know we have both limits being finite and that they exist, therefore. Then all of the following statements that we're going to talk about here are true. So the very first limit law, as x gets really close to some constant a, and if our function that we're considering is not actually like a function of x, but instead is just some constant c, then as x gets really close to a, that constant, it remains constant. It just stays itself, c. It's never changing. It's always constant. Now, because the title of this video is Limit Laws, Concepts, Theorems, and Proof, I just want to showcase this concept with a graph. So we have a function here, f of x is equal to 2. And I want to know, what is the limit of that function, which is just 2, as x approaches, let's say, -1. So what's the limit as x approaches -1 of 2? Well, here's my function in green. That's the function 2. And let's pretend as though maybe right about here is x equals -1. Now, as our x values get really close to -1, the corresponding y values for our function are 2. No matter how close we get to x equals 1, the y values are all going to be 2. So this is convincing to say, therefore, that the limit as x approaches -1 for our function y equals 2 must be 2. The y values are approaching a height of 2 as x approaches -1. So that's a pretty easy concept to get right there, hopefully. Not all of the limit laws will be that easily understood, by the way. So I don't want you to think that all of them are going to be that simple. They do have names, these limit laws. That's a limit of a constant limit law. However, you're not going to hear me say in any of my video series the names of these limit laws. I'm not a fan of naming things like that. Instead, I just like to know them intuitively and use them intuitively. The second limit law actually is pretty easy to understand. Let me say it out loud, and then you can probably hear how silly this limit law is. Hey, guess what? As x gets really close to a, I wonder what x gets really close to. Now that I've said that out loud, it should be obvious. As x gets close to a, this value of x gets really close to a, because x is getting close to a. I'm not even going to draw a picture of that. That one, honestly, most people get. By the way, these are not proofs. I'm not giving you proofs of these yet, because we do not have the mathematical technology to prove them. We need to have the precise definition of a limit to prove most of these. There's one of these that we can actually get away with proving, but the rest of them you cannot. That limit law is formally called the identity limit law. Going down to the next one. As x gets really close to a, x to the nth power here gets close to a to the nth power. And you could probably justify that a little bit by saying, well, of course, because x is getting close to a, therefore x to the n gets close to a to the n. However, there are some caveats here. Notice that the condition here says where n is a natural number. That's what that n double bar is. The capital N double bar is the set of natural numbers, which are the counting numbers 1, 2, 3, and 4, and so on and so forth. The reason why that's the caveat on this limit law is that suppose, just for a second, that n was allowed to be a non-natural number. Technically speaking, it could be a whole number or an integer, but let's suppose for a moment that it's a rational number. Specifically, let's suppose that n is 1/2. There's a problem if you're evaluating the limit as x approaches, let's just say -1 of x to the 1/2 power. As x gets really close to -1, you happen to know, because of your years in algebra, that the 1/2 power of x is the same thing as the square root of x. And this is a problem. As x gets really close to -1, you are taking the square root of negative numbers. And so this is why the power, or the exponent, for this limit law is currently restricted to be a natural number. Even though it doesn't actually have to be that restricted, it could be an integer. We're just, for right now, saying let's go ahead and pretend as though it's a natural number. This limit law is formally called limit of a power function law. I know, kind of a weird name, and I might have named these for this lecture I wrote last year. So if I did, I apologize for the terrible naming conventions. The fourth limit law is this guy right here. It involves radicals. So notice what we're doing. We're slowly increasing our way through algebra. We started with constants, and then we went from a constant to, actually, it wouldn't be that. We went from a constant to a linear function, then from a linear function to a power function, then from a power function to a radical function. So we're kind of growing through how we learned algebra as well. The limit as x approaches a of the nth root of x, and there is a condition on n there as well, is going to be the nth root of a. So far it looks like you could just plug a in for x, but that's not always true, so please do not believe that. The condition on n is that n is a natural number. There's also a condition on a. Because n is allowed to be a natural number, that means n could be 2, right? Well, if n is 2, you're taking the square roots of things. And if you're taking the square root of things, you better believe what you cannot take the square root of are negative numbers. And therefore, a has to be positive if n is even. If n is odd, you're okay. You could take the odd root of a negative number. So just heads up, keep in mind that you can't take the square root or even root of a negative number without stepping outside of the real number system. And for right now, let's just keep calculus in the real number system. Even though you can do calculus in the complex number system, I would just like to keep our calculus in the real number system for now. Let's see what our next limit law is. Actually, maybe I should name this one limit of a radical law. Isn't that cool? And this one actually is growing through our algebra there, because when you were in arithmetic, you learned about constants. And then when you entered into pre-algebra, you learned about variables, specifically x. Then when you went into elementary algebra, you learned about x squared, x cubed, and so on and so forth. After you dealt with the integer powers of x, or specifically the whole number powers of x, you then learned about radicals involving x. Then you stepped into intermediate algebra, or what we call algebra 2, and you learned about functions. This limit law is pretty easy because it's just telling us that if you have the limit as x approaches a of some constant times a function, well, because that constant is not dependent upon x, as x gets really close to a, that constant can be dragged outside of that limit. Because again, as x gets close to a, c, the constant, is unmoving or unchanged. So you can pull that out of the limit. It's probably one of the most important limit laws because you're going to use it all the time. So much so, you're going to use it without even knowing you're using it. Now this one I'd like to just give you a conceptualization for. Suppose that function is f of x. And let's suppose that we want to know the limit as x approaches some number. Let's make it easy on ourselves and just let x approach 0. Without loss of generality, let's just go ahead and assume that. So let me give you a value for that. Let's say that at 0, the function value is 1. That's what f of 0 is right there. Now, if I were to graph maybe 5, well, let's not do that. Let's graph twice f. Okay, so that blue ink right there, we're just going to pretend that's twice f of x. And I want to know, what is the limit as x is approaching 0 for that blue function, not the green function, but the blue function? Again, if that's twice f of x, then the y value right here at time 0 is twice what f of x originally was. It'd be 2. F of x was originally 1 at time 0. So as x is approaching 0 for our function 2 times f of x, it ends up being 2, which by the way is twice what the limit is as x approaches 0 for the original function f of x. As x approaches 0 for our original function, the y values are approaching 1. Same thing from the other side. However, when you take double the original function, as x is approaching 0 for the double function, you can see the y values are approaching twice f of x, which is 2. So that's a good conceptualization. It's not a proof, but it's just a visualization of the actual theorem itself. And again, I find that a lot of students are pretty okay with that. That is called the constant product limit law. Again, it is not an official name. Maybe it is, I'm not sure. Again, I don't memorize them. The next thing you learned when you're in intermediate algebra is how to add or subtract functions. Just like you learned addition and subtraction for arithmetic, once you learned about a function, you started adding and subtracting them. And this is also one of the most commonly used limit laws. We would say the limit of the sum or difference is the sum or difference of limits. That tends to be confounding for students when they hear that the first time. The limit of a sum or a difference, that's what this is right here. The limit of a sum or a difference of functions is, that's what the equal sign is, the sum or difference of the limits of functions. And that would be the sum or difference limit law. That's a really nice limit law. And remember, all of these limit laws require that the two functions in consideration, their limits both exist and are finite. So this does not work if the limits, if either of those limits are infinite or do not exist. Now you can see we're actually at the bigger limit laws now. We still have 4 left to talk about, but they're not too terrible. They kind of do basically what we've been doing. We can break things apart. I call this splitting limits. So you can split limits as long as those limits are finite, or in other words, they exist and are finite. So the next limit law is the limit of the product of functions ends up being the product of the limit of those functions. And again, that is the product of functions limit law. The next one is about the quotient of functions. So the limit of a quotient is the quotient of the limits. This is provided that the limit of the denominator, the limit as x approaches a of g of x, which is in the denominator, is non-zero. Otherwise, if that limit downstairs is approaching 0, you've got division by 0, and that's a problem. The last two are kind of the power and square root analog to what we wrote up here for just x. Rather than having x, we're going to have f of x. So let's take a look at those. The limit as x approaches a of a function to the nth power, where that function, remember, its limit as x approaches a is finite. Well, that is going to be the limit of the function raised to the nth power. Again, there is a condition here. N is a natural number. That does not actually have to be the case. And this limit law, in concert with the next one in line, allows us to basically grow this to say, well, n could be actually a rational number. So let's take a look at that next limit law, which is the limit of the nth root of f of x. Remember, if that's an even root, you've got issues, right? Because you want to make sure your function is non-negative. But with that in consideration, we can still talk about the limit law, which is that if you're concerned with the limit as x approaches a of the nth root of f of x, you can just move the limit inside of the nth root and evaluate the limit as x approaches a of f of x. Again, the condition on that is that n is a natural number and f of x is positive or non-negative. Technically, it should just be non-negative. Let me go ahead and put that in there. Non-negative if n is even. And I did mention something about these last two limit laws working in concert with one another to create kind of a bigger limit law. And that bigger limit law is essentially the following. The limit as x approaches a of f of x raised to the m over n power is equal to the m over nth power of the limit as x approaches a of f of x. This is provided that f is non-negative if n is even. Remember, if n is even, you're taking an even root there, and so f being negative is a problem underneath an even root. But those things kind of naturally come to you as you move through. The most important thing, in my opinion, is that you remember these limit laws can only work if those limits that you're looking at, those functions, limit as x approaches a of f of x and limit as x approaches a of g of x, those are finite. That's incredibly important. Otherwise, all bets are off and you cannot use any of these. That's sort of a lie. You can use the first one because it's just a limit of a constant. So there they are in their glory. And down below, I talk about the fact that we cannot prove them right now with the mathematical technology that we have. There is one that we can get away with proving. And this proof is for the power of functions limit law. And I got to tell you that it is so important to follow this proof because there's a proof style in here that's necessary for calculus. You learned it, or should have learned it, in your pre-calculus course. It is called proof by mathematical induction. So this is the theorem we're going to prove right here. It's the power of functions limit law. And remember, n is supposed to be a natural number, so that's what we're going to assume here. Now, when you do a proof, you get to assume the antecedent. So we're going to assume the antecedent, which is in our theorem, the if part of the theorem. It's if c is a constant, which we don't actually have a constant in that part of the theorem, so we don't have to worry about that. But we're going to assume that the limit as x approaches a of f of x and the limit as x approaches a of g of x are both finite. That implies they both exist. That's the only thing we get to assume here, other than the fact that we're also going to assume that n is a natural number because that's actually built into the power of functions limit law. Let's go ahead and do it. So let's let f be a function such that the limit as x approaches a of f of x is finite. Also, we're going to assume that whatever n we're dealing with, it's going to be a natural number. If you don't know this notation here, it's symbolic logic. You should have been taught that in your pre-calculus course. This means n is an element of the natural number system. Now, as you learned in your pre-calculus course, you can use mathematical induction to prove a lot of statements that rely on the natural numbers. Specifically in this case, we're going to go ahead and look at the first power of f. The limit as x approaches a of f of x to the first power, well, f of x to the first power is a silly notation. Nobody would ever use it. That's just the limit as x approaches a of f of x. However, I'm going to go ahead and use a silly notation again, and I'll say, but that we know, first of all, is finite. And for our argument, let's go ahead and actually say that this limit as x approaches a of f of x, since we know it's finite, let's just say that it equals some value L. That way we can speak the same language throughout this proof. So we have the limit as x approaches a of f of x to the first power is equal to, well, the limit as x approaches a of f of x. That's nothing new to us. However, we have assumed, we've been allowed to assume that the limit as x approaches a of f of x is equal to some finite number L. So I'll just say this is equal to some finite number L. But guess what? L is L to the first. And remember, L is just a fancy name for that limit. So this is going to equal that limit to the first power. And if you look at this, we have proven that at least for a first power, the limit as x approaches a of f of x to that first power is the same thing as the first power of the limit as x approaches a. So those two highlighted endpoints we've proven to be the same. Now with mathematical induction, you know from your pre-calculus, and I will continue to say that by the way, because if you had a pre-calculus instructor that did not cover mathematical induction, you need to email them and ask them to give you your money back. I'm adamant about that. I think that you're being cheated by instructors who are not teaching or doing their job. Most instructors are wonderful, by the way, but unfortunately, some slip through the cracks. All right, let's go ahead and assume that the claim is true for a natural number k. So assume the following. The limit as x approaches a of f of x to the kth power, where k is just some natural number, is equal to the kth power of the limit as x approaches a of f of x. We're going to make that assumption. This is the domino proof. We've proven it works for the first domino. We're supposing there's some kth domino down the line that is going to fall. What we need to do is prove that if it is true that that kth domino is falling, or that this claim is true for the kth case, then we need to prove that it must be true for the k plus first case. So let's look at the k plus first case. So we have this k plus first case. We know a little bit of algebra, and this is going to be a mantra that you're going to use all throughout calculus, is that you're going to do every prerequisite skill you can prior to doing your calculus. So we have a prerequisite algebra skill called the Law of Exponents, or the Laws of Exponents, that tells us that we can break apart a base raised to a power into the product of two bases raised to powers whose sum is the original power. That is hard for me to say, so let me go ahead and write that down. So there you see it. I just broke f of x to the k plus 1 into f of x to the k times f of x to the first. Now, we happen to have a limit law that I'm going to allow us to use. One of the limit laws that we have is that if you have a product within a limit and each of those subsequent limits are finite, you can break it apart. Let me write that down. Better yet, let me just showcase it. So what I'm saying here is you have the limit of the product of two functions. If each of those products, when you rip them apart into their subsequent limits, if each of those limits becomes finite, then you were allowed to rip those two apart into two different limits like we just did there. So in this case, can we break this limit apart into two subsequent limits? Well, let's see. And this is going to be often the thing that you have to do in calculus is you have to hope that you can break things apart. So let's go ahead and hope. That's the limit as x approaches a. I should really put a question mark. Is it the limit? Is it the limit as x approaches a of f of x to the k times the limit as x approaches a of f of x to the first? Well, the limit as x approaches a of f of x to the first, that is what we originally were handed. That is finite. We were allowed to assume that that is a finite number L. So that is okay that we broke that apart. But what about the left factor there? Is that finite? Is this business right here a finite number? Well, it is. It's a finite number because the limit as x approaches a of f of x to the k, we've assumed that's equal to the limit as x approaches a of f of x being raised to the k. And that, remember, is just the limit, that is just L. And then raised to the k. And L is a finite number. So that is L to the kth power, or in other words, a finite number as well. Thus, this splitting of the product of these two functions into two separate limits is legal. It's totally fine. You can totally do it. Great. Not only that, but I've just written down what the left factor will turn into. The limit as x approaches a of f of x to the kth power is going to turn into L to the k. And I can erase the question mark because I now know both those limits are finite. Times, and we know that this guy right here from above is L. And this is going to be, remember that's L to the first, so this is going to be L to the k plus first power. And remember what L is. L, according to our handwriting up above, is the limit as x approaches a of f of x. So what did we just prove? Because we did just prove something. We've proven that, first of all, the claim is true for the first power. So the limit as x approaches a of f of x to the first is the same thing as the first power of the limit as x approaches a of f of x. We've proven that. We've also assumed that the claim is true for some arbitrary kth natural number down the road. That's like assuming that you have a domino that's falling in the future. But with that assumption that domino is going to be falling in the future, we have proven that the next domino in line has to fall as well. That is, that the claim is true for the next domino in line. If a domino falls, the next one has to. And that domino that's falling is arbitrary, so this means every domino is going to fall because we've already proven the first one is, so therefore the second has to. But because the second has to fall, the third one has to. Because the third has to fall, the fourth one has to, and so on and so forth down the line. So thus, the limit as x approaches a of f of x to the nth power is the same thing as the nth power of the limit as x approaches a of f of x for n in the natural numbers. Because, by the way, mathematical induction pretty much is usable only over the natural number system, or subsets of it, or the natural number system plus a few other numbers, but pretty much the natural number system. And whenever you finish a proof, it's good to tell the world that you're done with it. So I'm going to write QED. If you have not been a student of mine in the past, you don't know, but that is Latin, quod erat demonstratum. It means, so it has been demonstrated. Now, in my lecture notes, I say before we get too far, but in this video, I'm going to say before I let you go, because this is the very last page for this video. It's essential to focus on the fact that the limits, these limits right here, must both exist and be finite before being able to apply any of the limit laws. That is critical. With that being said, I hope this video helps out, and I hope you stick around for the next video in line. Have a great day.
the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.